Hello students, welcome to the EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics. Today we are going to talk on the module D'Alembert's Principle and Lagrange's Equations under the paper Classical Mechanics. After completing this module, you will be able to learn about a formalism in mechanics which is based not on Newton's law but on D'Alembert's principle. You will learn that this formalism is particularly convenient for constrained systems, that is, systems which move under forces which are constraining it. Newtonian mechanics is based on Newton's laws of motion. In many practical problems, it becomes difficult to set up Newton's equations and solve them, particularly in the presence of constraints. In such cases, an alternative formalism is needed to simplify the analysis of the system. In this unit, we will discuss one such alternative formalism which is based on D'Alembert's principle. In this context, we will first introduce the concept of virtual work. What is virtual work? So the principle of virtual work says that if a system of n particles is specified by the coordinates Ri, then virtual displacement is defined as an imaginary infinitesimal displacement delta Ri at a fixed given time t, which means that the coordinates are represented by the vector Ri, and we imagine that there is an infinitesimal displacement of these coordinates at a given time t, while the displacement satisfies the constraints and the generalized velocities qk dot. They are kept fixed at time t. The virtual displacements, when represented in generalized coordinates, automatically satisfy the constraints. The relation between the infinitesimal displacement of the generalized coordinates and the virtual displacement is given by the chain rule, because each coordinate position or coordinate vector Ri can be represented as a function of the generalized coordinates Q, set of Q's. Therefore, delta Ri is small deviation in the Ri can be represented as sum of displacements by the chain rule, namely delta Ri is summation over j partial derivative of Ri with respect to the generalized coordinates qj into the deviation in the generalized coordinate qj for all values of j. Let Fi be the total force acting on the ith particle. That is, it is the sum of the external applied force plus the force of constraint, if any, on the ith particle. As the system is in equilibrium, the virtual work, which is defined as the work done on the system by all the forces that act on the system when the system undergoes a virtual displacement represented by the set of displacement delta Ri. That is, the total virtual work done on the system is delta W is the sum of Fi dot delta Ri, where delta Ri is the virtual displacement of the ith particle and Fi is the force acting on the total force acting on the ith particle, where the total force Fi acting on the ith particle is sum of the applied force plus the constraints force, if any. If we now restrict ourselves to systems for which the net virtual work done by the constraint forces is zero, that is, if the system evolves in such a manner that the work done by the constraint forces is zero. In fact, this is, if you remember in our example of a motion on the inclined plane, the constraint force is normal to the plane and the motion is along the plane, therefore it does no work. So generally the situation is that the constraint force does not do any work on the system. That is, the work done by the constraint force sigma over I Fi constraint dot delta Ri is equal to 0. So therefore, the virtual work done on the system is simply given by the applied force, and delta W can be written as the sum of the work done by the applied force on the ith particle, namely sigma over I Fi applied dot delta Ri. Thus, the total virtual work done on the system is only by the applied forces. This is the principle of virtual work, and it's an important principle. We will now discuss what is known as D'Alembert's principle. It says that the total force acting on a particle is the sum of the applied and constrained forces. Then the virtual work done by the constrained force is 0, and we have seen that the virtual work done on the system is simply delta W is equal to work done by the applied forces, and we have dropped the superscript applied from the force. So delta W is sigma over I Fi dot delta Ri, where Fi now stands only for the applied forces. And we have removed the constraint forces from our discussion altogether. Now from Newton's second law of motion, the rate of change of momentum of a particle is equal to the applied force. Thus, Fi is equal to dpi by dt is pi dot. Then we have delta W, that is virtual work done, is equal to pi dot delta Ri, and from the equation 2.5, the Newton's second law, this delta W can be written as Fi minus pi dot delta Ri is equal to 0. This is the D'Alembert's principle. It says that the rate of change of momentum is determined only by the non-constrained forces. So this is a generalization in some sense, and this has arisen because of the fact that our constraints are assumed to be such that the constrained forces do not do any work. This principle can be generalized to relate the generalized forces to the rate of change of momentum. See, we have stated the principle for the applied force, but this can be easily generalized to the generalized forces. In terms of generalized coordinates, we have the work done delta W is sum over J of Fj into delta Qj, where Fj is the generalized force acting on the coordinate J, the generalized coordinate J, which, and delta W is then, if written as pi dot delta Ri, and since the position vectors Ri are functions of generalized coordinates, then delta Ri can be related to the variations in the generalized coordinates by the chain rule. So delta W is equal to sum over J into generalized force Fj multiplied by the displacement delta Qj, which can in turn can be written as sigma over I pi dot delta Ri equal to then pi dot, then delta Ri is partial derivative of Ri with respect to dQj with respect to Qj into delta Qj sum over J also. Now, the generalized force Fj we have defined as Fi dot dri by dQj, which is equal to ratio of the change in the work done divided by a change on the generalized coordinates, which is equal to then from the above equation pi dot dri by dQj. So in equations given above, I runs from 1 to n and j stands for the generalized coordinates. So j runs only from 1 to 3n minus k. Thus the generalized force on the jth particle can be calculated from the non-constraint applied forces alone through this equation that Fj is equal to sigma pi dot dri by dqj sum over all I. We are now ready to obtain very important equations which are alternative to Newton's equation of motion, which we have mentioned earlier in the introduction, namely the Lagrange's equation of motion. Now remember, the kinetic energy of a dynamical system is defined as sum of the kinetic energy of each particle. If a particle mass mi has a velocity vi, its kinetic energy is half mi vi square, and vi is a vector which is just dri by dt. Therefore, the kinetic energy T is defined as, or for the system, as 1/2 sigma over I mi into ri dot ri dot. Ri dot is the velocity, and dot ri dot is the velocity square. So, the kinetic energy then can be written as what? As a function of qj dot and t. This functional relationship. So, why can we write it in this way? Because remember, the position vector is related to the generalized coordinates. So, Ri is a function of the generalized coordinates qj's. So, Ri dots are also functions of qj dots and qi. So, the kinetic energy is a function of qj dot and t, time. This functional relationship of t can be seen by remembering that the position coordinate Ri can be written in terms of generalized coordinates, and Ri dot is obtained by taking the total derivative of Ri with respect to time, and which is a function of qj dot. Therefore, we can write the partial derivative of the kinetic energy T as dt by dqj is equal to sum over I mi ri dot dri dot by dqj. But remember, mi ri dot is pi. Therefore, this is in turn is equal to sigma over I pi dot dri dot by dqj. Likewise, dt by dqj dot is equal to mi ri dot dotted with dri dot by dqj dot, which is equal to pi dot dri dot by dqj. Why? This happens because dri dot by dqj is equal to dri dot by dqj dot. Now, this can be easily proved by noting that delta Ri, that is a variation in Ri, is equal to sigma over j partial derivative of Ri with respect to qj into delta qj. Now remember, Ri dot is equal to dri by dqj into the total derivative of qj with respect to t plus the partial derivative of Ri with respect to t. Now, taking the partial derivative of this equation, that is of Ri dot with respect to qk dot, we have dri dot by dqk dot is sum over I dri dqj, then partial derivative of qi dot with respect to qk dot is simply equal to delta jk. So this is just delta jk, which is equal to dri dot by delta qk. Now, differentiating the equation given earlier 212 with respect to t, we get the total derivative of d dt of the partial derivative of t with respect to qj dot is then equal to sigma over I pi dot dri by dqj plus sigma over I pi dot ddt of dri by dqj. The first term in this equation, namely pi dot dri by dq, can be identified as the generalized force acting on the jth particle. In the second term, we have ddt of the partial derivative of the position vector of the ith particle with the jth generalized coordinate. So ddt of dri by dqj, which can be written as dd or partial derivative with respect to qk of dri by dqj qk dot plus the total derivative with respect to time of dri by dqj, which becomes a partial derivative with respect to qj of the sum of two terms, namely sigma over k dri by dqk qk dot plus dri by dt, which then is equal to dri dot by dqj. Therefore, ddt of dt dqj is equal to dt by dqj plus the generalized force F acting on the jth generalized coordinate. We therefore have a generalized equation of motion given by ddt, that is total and time derivative of the partial derivative of kinetic energy with respect to generalized jth velocity minus the partial derivative of the kinetic energy with respect to the generalized position qj is equal to fj. That is ddt of dt dqj dot minus dt by dqj is equal to fj is the generalized equation of motion. Now, if we specialize to the conservative forces, and if you remember that conservative forces are those forces which can be obtained from a potential function u by taking the gradient of the potential function. So for conservative forces, one can define a potential function u which is a function of the position coordinates, then the force acting on the force F is simply equal to minus the gradient of this potential function u. That is, Fi is equal to minus gradient I acting on the potential function u. Now just notice that this I, the subscript I on the gradient and force, stands for the force on the ith particle, and the gradient is taken with respect to the coordinates of the ith particle. Now the generalized force Fj is equal to sum over I of the applied force dot dri by dqj, which is equal to, then the applied force is given by conservative force by the gradient. So this is given minus gradient I u of rk dot dri by dqj. Now the force Fj is du by dqj. Therefore, the generalized equation of motion obtained by using D'Alembert's principle expressed in generalized coordinates then becomes ddt of dt by dqk dot minus dt by dqk is a minus du by dqk. So this is what we obtain as the generalized equation of motion, or equation of motion in terms of the generalized coordinates. Now, which has reference only to the expressions for the kinetic energy and the potential energy given in terms of the generalized coordinates. So if we can write for our dynamical system, if you can express the kinetic energy of the system and the potential energy of the system in terms of generalized coordinates, then the equation of motion in terms of these generalized coordinates is simply given by this equation, that is the total time derivative or the partial derivative of t with respect to qk dot minus the partial derivative of t with respect to qk is equal to minus du by dqk. Now, we define a function called the Lagrangian, which is defined as the difference between the kinetic energy and the potential energy. Remember that for holonomic systems, we have the constraints which are independent of the generalized velocity. So for the holonomic constraints, u does not depend on the generalized velocity. That is, the partial derivative of u with respect to generalized velocity qk dot is equal to 0. Now this allows us to write the equation which we gave earlier as the generalized equation of motion in terms of the kinetic energy and potential energy and their derivatives. Then since u for holonomic constraints is independent of the generalized velocity, this allows us to write down the equation of motion in terms of generalized coordinates in the form that d dt, that is the total derivative with respect to time of this quantity Lagrangian, of the partial derivative of Lagrangian with respect to the generalized velocity k, that is qk dot, minus dl by dqk is equal to 0. This is a very important equation, and this is an equation we will make use of subsequently. And this is the well-known and the famous Euler Lagrange's equation for each generalized coordinates qk. So what it means that if we are, for a dynamical system, after specifying the number of degrees of freedom, then choosing the appropriate generalized coordinates which are equal to the number of degrees of freedom. So once we have chosen these appropriate generalized coordinates, and if further our system is conservative and holonomic, then the potential energy of the system does not depend on the generalized velocity, and in that case we can define a quantity called the Lagrangian, which is the difference of the kinetic energy minus potential energy, each written in terms of only generalized coordinates and their velocities. And then the equation of motion is simply given for generalized coordinates and are given by the Euler-Lagrangian equation of motion, and state the ddt of dl by dqk dot minus dl by dqk is equal to 0. Let's now consider the time and velocity dependent potential. So far we have considered potentials which do not have time and velocity dependence. Say in defining the Lagrangian, we have confined ourselves to potential energy which does not depend on time. We may have situations, in fact, where the potential energy, even though depends on time, but is conservative at each instant of time. What we mean by saying that it is conservative at each instant of time is that the energy is conserved at every instant of time. This could be the case, for example, in the case of planetary motion about the center of a mass. If the potential is velocity dependent, the Euler-Lagrange's equation may not hold in general. In case we have generalized force that can be written in terms of velocity dependent potentials, such force we'll call a generalized potentials called generalized potential energy. That is, if we can we can drive generalized force in terms of the generalized potential energy. In this case, the potential energy will depend not only on the generalized coordinates but also on velocity. And if this generalized force can be determined through an expression of the type Fg is going to minus du by dqj plus the total time derivative of du by dqj dot. The Euler-Lagrange equation still holds for the Lagrangian t minus u, when u is defined in this way. The u defined in this way is not the potential energy in the conventional sense of being the work done by a generalized force. That it cannot be calculated from the line integral of the generalized force. But this concept of the generalized potential still allows us to use the concept of Lagrangian to obtain the Euler-Lagrangian equation of motion, and that is the usefulness of this formalism. As an example of velocity-dependent force, we will take the well-known example of Lorentz force on a charged particle. If you remember that the Lorentz force on a charged particle in the presence of electromagnetic field depends on the velocity of the particle. So we consider this a special case and obtain the corresponding Lagrange's equation. Now in case the potential energy depends on the velocity, that is if we have a velocity and time dependent potentials, we have mentioned that what changes occur. So as an example, we'll now obtain the Lorentz force equation, or rather using the Lorentz force equation, we'll obtain the Lagrangian. We know that the equation of motion of a charged particle of mass m and charge q in the presence of electromagnetic field is given by m into d2r by dt square is equal to Lorentz force, which is q times the electric field E plus 1 by c v cross b, where v is the velocity and b is the magnetic field. The electric and magnetic field, we know, in turn can be expressed in terms of the scalar and vector potentials A through the well-known relations from the study of electricity and magnetism, namely that B is equal to curl of A and E is equal to minus grad phi minus 1 upon c dA by dt. That is, instead of the 6 components of 3 for electric and 3 for magnetic field, these 6 components are not all independent, and we can represent the electric field and magnetic field in terms of a scalar potential with 1 component and a vector potential A with 3 components. Then written in terms of this, we can express the equation of motion as, for the x component, for example, mx double dot is q times the x component of the electric field plus 1 by c times the x component of the quantity v cross b. Now, x component of the electric field is given by minus ddx of phi minus 1 upon c ddt of x component of the vector potential A, and x component of curl of B can be easily calculated. Curl of V cross B can be easily calculated. So we have mx double dot, the equation of motion is equal to q times minus d phi by dx minus 1 upon c dx by dt plus 1 by c v cross into this x component of this. So del cross B x component. Therefore, the x component of the equation of motion is mx double dot is equal to q times minus ddx of phi minus 1 upon c of ddx of x component of the vector field A plus 1 by c v cross b. B is, in terms is curl of A. So this is x component of v cross curl of A of x. The x component of this quantity v into curl of B can be easily calculated, and we find that the x component of v cross curl of A is given as vy into day by dx minus dx by dy minus vz into daz by dx minus daz by dx. Then substituting in the equation of motion for the x component, mx double dot becomes equal to q times minus d phi by dx minus 1 upon c da by dt plus 1 upon c vy day by dx minus da by dx, and similarly for the z component. Since vector potential depends on the coordinates and time, because the vector potential is a function of x, y, z and t, Then we can write the vector potential A being a function of the coordinates x, y, z and time t. Therefore, 1 by c of the total derivative of the x component of the vector potential with respect to time by the chain rule is then equal to 1 upon c dx by dt plus 1 upon c multiplied by vx into dx by dx plus vy into dy by dy plus vz into dax by dz. Now substituting for the partial derivative of the x component of A with respect to time in the equation 2.29 from 2.30 and adding and subtracting the quantity Vx into dAx by dx, we can write mx double dot as equal to q into minus d phi by dx minus 1 upon c, the total derivative of ax with respect to t plus 1 by c v dot, the partial derivative of the vector potential A with respect to x, and opening this we can write this to be equal to q times minus ddx of phi minus 1 upon c v dot A plus ddt of d dvx of phi minus 1 upon c v dot A. So in deriving the above equation, we have used the fact that the partial derivative of the velocity with respect to the coordinate is 0, as for example dv, as the velocity does not depend on x explicitly, and d phi by dvx is also equal to 0 because phi is a function of x, y and z. It does not depend on the velocity. Therefore, ddt, the total derivative of v dot A with respect to time, is equal to the total derivative of ax with respect to t, dax by dt. We can thus write the x component of the force Fx is equal to mx double dot is equal to minus du by dx plus the total derivative with respect to time of the partial derivative of u with respect to vx, where u is now defined as q times the scalar potential phi minus 1 upon c, the dot product of velocity and the vector potential A. So this is a kind of generalized velocity dependent potential. And in that case, the Lagrangian of the charged particle in the presence of electromagnetic field can be written as L is equal to T minus U, where U is given by the quantity I just mentioned. Therefore, the Lagrangian for the charged particle in the presence of electromagnetic field is equal to T minus Q into phi minus 1 by C V dot A. Well, this is an important result. We will illustrate what we have learned with the help of an example. The example we consider is the example of a particle which is moving under gravity. So you have elliptical wire type which is in the vertical plane, and this in this plane I have the coordinates say x and y. So the particle m is constrained to move under gravity in this elliptical wire in this xy plane. Then obviously the constraint equation is that x square by a square plus y square by b square is equal to 1. Now we can easily parameterize this by a single angle theta cosine by an angle theta by writing x is equal to a cosine theta and y is equal to b sine theta. Why? Because on the ellipse x and y are related. So if x is equal to a cos theta and y is equal to b sine theta, you can immediately see that x by a whole square plus y by b whole square is equal to 1, which satisfies the constraint of the equation. So there is only one generalized coordinate theta to be considered. So in terms of these generalized coordinates, we can then write down the kinetic energy. Remember that the kinetic energy is 1/2 mass times x dot square plus y dot square. But now since x and y can be represented in terms of parameter theta, then the kinetic energy takes the form half m a square sin square theta, theta dot square plus b square cos square theta, theta dot square. And the potential energy U, which is equal to mgy in the Cartesian coordinates, can be written as mgb sin theta. Now the generalized force using this potential energy can be easily obtained by the expression that the generalized force corresponding to the generalized coordinate theta, f theta, is equal to minus du by d theta, that is partial derivative of u with respect to theta, and is equal to minus mgb cosine theta. Having defined the generalized force acting on a particle moving on elliptical wire, which is represented in terms of only one generalized coordinates theta, the equation of motion then is given by ddt of dt d theta dot minus dt by d theta is equal to the generalized force, which is given in terms of the generalized potential du by d theta. Now, from the expression of the kinetic energy, the partial derivative of the kinetic energy with respect to theta dot is equal to half into mass into a square sin square theta plus b square cos square theta 2 theta dot, and the partial derivative of d of the kinetic energy t with respect to theta is equal to m theta dot square into a square sin theta cos theta minus b square sin theta cos theta, which can be simplified to m sin theta cos theta into a square minus b square theta dot square. Thus, the equation of motion of a particle moving on an elliptical wire is simply given by theta double dot is equal to minus g times b cosine theta divided by a square sin square theta plus b square cos square theta. And now you can see that for a circular wire where a is equal to b is equal to r, the radius of the wire, the equation of motion for a particle moving on a circular wire under gravity is simply given by theta double dot is equal to minus g times cosine theta by r. So you can see that in terms of the generalized coordinates, the equation of motion is quite simple. So students, let's summarize what we have learned in this module. In this module, we have learned that for conservative systems, by conservative system, let me explain once again, means where the energy is conserved. Generalized force for conservative systems can be obtained from the potential energy function expressed in terms of generalized coordinates as the generalized force corresponding to the generalized coordinates qj is fj is equal to minus the partial derivative of the generalized potential with respect to the generalized coordinate qj. Now the D'Alembert's principle states that the rate of change of momentum is determined only by the non-constrained forces. Thank you.